Good evening and welcome to Science at the Theater, sponsored by Berkeley Lab's Friends of Science and co-sponsored by UC Berkeley, Chabot Space and Science Center, the Exploratoria, and the science departments of Berkeley, Albany, and Oakland High Schools. We're also pleased to receive the support and encouragement from the Berkeley Repertory Theater for these talks on science. We thank them as well. I'd like to tell you a little bit about our speaker. Paul Alivisatos is internationally recognized as one of the world's leading researchers in nanoscience. He led the development of the lab's Molecular Foundry, a nanoscience research center, until its establishment in a new building and with the appointment of a permanent director in 2005. Paul received his bachelor's degree in chemistry from the University of Chicago in 1981 and a PhD in physical chemistry from the University of California, Berkeley, in 1986. He then went to AT&T's Bell Laboratories, where he was a postdoctoral fellow with Louis Brune. In 1988, he joined the University of California at Berkeley as a faculty member and professor of chemistry in the Department of Material Sciences and Engineering. He also serves as an associate laboratory director for physical sciences at Lawrence Berkeley National Laboratory and director of the Material Sciences Division. He has received many honors and awards. Recently, the 2007 E.O. Lawrence Prize from the U.S. Department of Energy, which he shared for materials research for his work in the chemical synthesis and characterization of functional semiconducting nanocrystals, also known as quantum dots, and the 2006 Eni Italgas Prize from Premio Italgas Energia and Ambiente, excuse my pronunciation, which he shared for studies on next-generation solar cells. Over the past 10 years, he's received many honors and awards. He is a fellow of both the American Physical Society and the American Association for the Advancement of Science, and in 2004 was elected into the National Academy of Sciences and the American Academy of Arts and Sciences. Not only is he highly acclaimed for his research and academic roles, but Paul Alivisatos is also a scientific founder of several startup nanotechnology companies, including Quantum Dot Corp and Nanoscience, Inc. His role in these companies is critical to realizing the commercial potential for the technologies that he has developed. And for the past 2 years, Paul has been working on the Helios Project, a project for solar-based sources of energy. This project will attack the renewable energy problem in a technical approach reminiscent of Bell Lab's development of the transistor. And Paul is leading the Helios Project's materials section. Paul?
Thank you very much, Terry, and it's really it's a fantastic honor to be here and to have a chance to talk to you today about the aspects of nanomaterials that relate to renewable energy and to solar energy. A few weeks ago, Steve Chu, the lab director, had a chance to talk to you about the overall Berkeley Lab energy research strategy, and the laboratory is trying to have an impact on essentially every aspect of energy utilization from the demand, supply, and modeling and consequences side. And today, we're just going to be speaking about one little piece, which is a piece right here concerning the applications of new materials in the use of energy. Now, let's start this discussion by putting it into a context. And I presume most of you, when you took a class in biology or earth science as a student, had to learn all of these cycles. There was a carbon cycle, a water cycle, nitrogen, everything had a cycle. There were just lots of cycles. And learning them all was actually quite a bit of a chore. And what I'd like to just remind you of is that there's a reason that all those cycles occur, and it has to do with the fact that if you start to manipulate the composition of materials on a global scale, so you really start to matter in terms of the size of the entire planet, then you can't really run a half of a cycle. Because, for example, if you burn fuel like hydrocarbon, like our gasoline, if you burn that and produce carbon dioxide by reacting it with oxygen, that releases energy. That's how we get a lot of our energy today, and it produces carbon dioxide. But if that then just stays there in the atmosphere and it accumulates, then over time, that starts to generate basic trouble. And you can argue all the details of this that you like, but fundamentally, you can just go back to your intuition and you know that all of those cycles that we were learning about are concerned with systems which are sustainable over the long term. And the moment you start to have half of a cycle in a way that is on global scale, then you really start to create possibility of a system which isn't completely sustainable. So there's a very fundamental issue there in terms of we need to develop a full cycle. We can't just take the fuel and burn it and put out carbon dioxide. What we need to be able to do is to take the carbon dioxide in one scenario and have it react with water and go backwards and make a fuel. Could we do that? Could we make a complete cycle in which instead of just burning the hydrocarbon, we could take the products and then bring them back and create the fuel again and make a complete cycle? That's what a plant can do. Can we do that? So the Helios program has an extensive activity in solar fuels, and the goal of it is to complete the combustion cycle. And if we think about sunlight plus CO2 and water and trying to take those to produce a hydrocarbon or ethanol or any such energy-containing molecule, then we can imagine different pathways for going from one side to the other. For example, we could do it with plants, and that could make cellulose, and then the cellulose can be broken down to make ethanol. And this kind of pathway is what Jay Kiesling will be talking about in the next lecture in this series. But today we want to consider the possibility of using artificial materials, not using plants, not using biofuels. We want to think about the possibility of, could we use an artificial system of materials which could perform the function that a plant does to take carbon dioxide and water and combine them to make a fuel? Could we do that with a completely artificial system, and why would we want to, and how well will it work? So first, let me just remind you that the goal then, our goal is to make a liquid fuel, and I just want to remind you that the reason that we'd like to make a liquid fuel is because liquid fuels are very energetically dense. So for example, here you can see the stored energy per unit weight and per unit volume, and you can see that something like gasoline is a fairly high energy density compared to, say, batteries like nickel metal hydride or lithium ion. So if we want to take the energy of the sun and ultimately store it in a form that's transportable, we'd like to store the energy in a system like gasoline or something of that type, which has a high energy density and is transportable. That's the goal. And as I've mentioned to you, there's two different, very different types of approaches. For example, you could use a system that uses plants or microbes in order to do that, and that would be a kind of biofuels approach. Or you could use materials, and as I'll try to show you today, when we think about using materials, for the most part, we think about using materials which have been controlled and patterned on a very small length scale, or nanomaterials. And the reason for that, as I'll try to explain to you today, has to do with the scale of the solar fuel problem. In other words, if we try to imagine materials with which we would make solar fuels, the scale on which we require to make those fuels is enormous. And that's going to impose some constraints on the system with respect to the kinds of materials we can use. And also, we need to have a certain ultimate efficiency. So I'd like to just describe to you today how nanomaterials could contribute to a solution for making fuels from the energy of the sun with carbon dioxide and water. So a lot of our thinking hinges on an understanding of how much land we would have to use. That's a kind of a first step. So in this graph, what I've shown is the energy consumption of the United States. We consume power of 3.3 terawatts. The exact number isn't totally important for you, but imagine for a moment that we have a certain piece of land, and that land is sitting there with sunlight incident on it all the time, and that sunlight contains a certain amount of energy. So we can imagine taking that energy from the sun and converting it into the energy of molecules. So we'll put that energy ultimately into a fuel like, say, ethanol. Okay, imagine that we created ethanol from the energy of the sun at a certain power efficiency. So we know how much energy is incident from the sun, and we know how much energy is stored in a gallon of liquid. So we can say for every photon incident, what efficiency do we convert that into the fuel? So that would be shown here in these lines, 1%, 3%, 10%, for the power efficiency of conversion. And then here we show the area in land. So for example, let's take an area equal to the idle cropland in the United States, and imagine that all the sunlight incident on that area, a certain fraction of that energy is converted into fuel, like 1%. So at 1% energy conversion efficiency for an area of 58 million acres, that produces enough energy to be equal to the amount of gasoline that we use in the United States today. If we're up at 6%, that would correspond to all of our energy usage. So what this means is that if we had an area of 58 million acres devoted ultimately to energy conversion, and if we could perform that energy conversion at 6% efficiency from photon to fuel, then we would be able to replace all of our energy consumption, everything. And at 1%, we could replace all of the gasoline. So there's good news and bad news in this. 1 and 6% don't seem like such outrageous numbers, but 58 million acres is an awful lot of area. And so you can think about it either way. But the goal of this project is to create a system out of artificial materials. Now, when we say 58 million acres, that is in fact an amount that can be cultivated for agriculture, but there's really not much example of making an energy conversion system out of artificial materials on that large of a scale. So we have a daunting challenge, and so we try to dig into it now and see, is it possible, and what are the constraints, and how could we go about doing it? Just to give you a feeling for how big is 58 million acres, these green boxes correspond to 58 million acres, so that's how much area would be involved. Or for example, this kind of orangey box in the desert here, that would correspond to a box proportionate just for California. So if we had an area of that size out in the desert, say, for example, consisting of nanomaterials, and if it could convert the energy of the sun into gasoline at 1% power efficiency, then that would replace all of our electricity use, and at 6% power efficiency, it would create enough energy for all of our energy use. Okay? So that gives you a feeling, at least, for the sizes. They're very large areas, without question. Just because they're shown in boxes like these doesn't mean that that's how they would be done. And to give you some calibration, 58 million acres is also approximately equal to all the roads and all the roofs, if so, in the United States. All the roadways and all of the roofs, that's about 58 million acres. So that gives you a feeling, at least to some degree, for the amounts of areas we're talking. They're significant, but they're not by any means out of the question. Now, in today's talk, dominantly, I'm going to talk about the conversion of the sun into electricity, but then towards the end, I'll talk about the conversion of the electricity into molecules, only because just this part takes quite a bit of thinking, and so let's just do this part first, and then we'll move on to the next. Now, many of you know that you can buy a solar cell and put it on your roof today. Indeed, it's a fine idea to do it. And so we could say that in some sense there's a technology already that takes the energy of the sun and at least converts it into electricity. And in fact, if you can really pull out all the stops and engineer it very carefully, then one of these kinds of solar cells can have an efficiency from photon to electricity, only to electricity yet. It hasn't gone to a fuel, but just to the stage of electricity. That can have a power efficiency in the neighborhood of 22 to 24% from the photon to the electricity. So in some sense you could say, well, this is a solved problem. But what I'd like to show you is that there's much more to it, and it's much richer than just what we've seen so far. And part of that is because it's really hard to make enough of these. And I think you can understand that. It is quite difficult. There's a shortage right now of the materials. And even if there weren't, the processes by which we make these are perhaps not the best ones we could imagine when we really want to do it on an enormous area beyond the numbers of rooftops that we do presently. So what I'm going to try to suggest to you is that there are new phenomena which occur with very small crystals instead of these enormous ones. And when we think about making solar cells out of those, possibly they could be scaled to much larger areas, and possibly also they could have improved performance. So let's just look a little bit about how a solar cell works. There's a piece of crystal, and sunlight is incident on it, and we can think of the photon as a particle that comes in. Ooh, that's kind of surprising. Okay. I didn't have that part on when I played it for myself. Okay, so a red photon, that was just a red photon. That means it's a very long wavelength, low energy photon, and it kind of went right all the way through that crystal. It didn't get absorbed. And next what we're going to see is a yellow photon that comes in. The crystal has in it electrons which are holding all the atoms together. And if the photon has enough energy, it can dislodge one of the electrons and pop it off into what's called the conduction band, which means that it's an electron that's free to float around and to be collected. Now, I want to give you an analogy here. Let's imagine that I have a ball, okay, and up here there's a long wall, and on the wall there's a shelf, just one shelf, okay, so I take the ball and I throw it up, and it hits the wall, and I throw it delicately enough that it doesn't just bounce away. It kind of falls down that wall and hits the shelf and lands there. Then I would have stored some energy by throwing that ball up. It lands and it stays on that ledge. And so that's a certain amount of energy that's stored. Now, if I throw the ball up higher, I'll still only get the energy of the ledge when it falls down to the height of the ledge. So no matter how high I throw up that ball, when it falls down and hits the ledge, that's how much energy that I've collected. That's basically what happens in a so-called semiconductor material. It's a system which has energy levels, and we can take electrons and toss them up a wall and have them fall down to the ledge. That's the lowest energy that an electron can occupy in the crystal. So if a photon comes in and poop, it pops an electron up to a high energy. If it has just enough energy to reach the ledge, then I can collect all the energy of that photon. If, on the other hand, the photon has a little bit more energy, for example, instead of a red photon, it's a green or a blue one, then when the photon comes in and gets absorbed, it does more than promote the electron up to this minimum level. It goes up higher, and then when it falls down, that excess energy there between the energy of the photon and the energy of the ledge is lost to heat. That's why if you have a solar cell and you put it out in the sun, it is collecting electricity, but also gets hot. Okay? And that part where it gets hot is not the energy that we're really interested in. Of course, you could use the heat, but the heat's not quite as useful a form of energy as the electricity itself is. So one of the things that we face in a conventional solar cell is we have to decide what gap should we make for this solar cell. In other words, how big should the energy gap be between the highest occupied and lowest unoccupied levels of the crystal, such that when light gets absorbed and then it falls down to this level, we lose some as heat. If I make this gap really small or really large, it will affect the performance of the solar cell. And that's shown a little bit here with the different colors of light. If I have a solar cell with a really small gap, it will absorb all the colors of light down to very low energies. But you won't collect very much energy because the photons will promote the electrons, but then they'll fall down to this small level, and the gap in energy won't be very big. So you can make the gap bigger and bigger and bigger and collect more and more and more energy up to a certain maximum, and that maximum occurs because now, remember, all the photons below the gap don't get absorbed. They go right through the crystal. And so you have to match the solar spectrum to the gap of your semiconductor material, and when you map them just right, and if you're very lucky, then you can pick a gap of around 1.1 electron volts. That's near the gap of silicon. And if you do everything just right, you can collect 31% of the energy of the sun as electricity. The rest lost as heat. And you can't do any better than that if there's only one band gap inside the semiconductor. It's just a limited process. That's all that you can do. Lower energy photons go right through the system. Larger energy photons deposit energy as heat, and you exactly collect all the energy of the 1.1 electron volt photons. Now, this has been a topic that people have studied for many, many years, and they've said, well, okay, I can just make 3 solar cells instead of 1. And you can. You can make a solar cell, for example, out of germanium, and 1 out of gallium arsenide, and 1 out of gallium indium phosphide. You could take these 3 elements, and each one has a different band gap, and you wire each one up separately so that you could collect the energy from the very red part, the green part, and the blue part of the spectrum separately. And when you do that, you lose less energy into heat. So these kinds of solar cells have power efficiencies in the 35 to 40% efficiency range. And in fact, they are used in satellites where it's at a premium to get the highest efficiency possible for the area and the weight that's available. The problem is that when you make all of these semiconductor materials, one attached on top of the other, the way in which you make them looks a lot like the way that you might make, say, a computer processor. And it just doesn't scale very well. You can't really do that on the enormous areas that you would like in any cost-effective kind of way. And on top of that, you face an additional problem, which is that some of these elements that you use in these multi-gap solar cells are not abundant enough to actually coat 58 million acres. There's just not enough of it out there in the world. So there are just huge problems if you try to extend this idea of multi-gap cells with the bulk materials that we have available to us today. If you try to extend those to making solar cells for really widespread utilization. So the lessons from satellite solar cells are very interesting, but they don't really scale to huge areas. I do say this 50% question mark. DARPA, the Defense Advanced Research Projects Agency that you may have heard of, currently is running a project to try to make a 50% efficiency solar cell out of a multi-gap kind of system, and probably they'll succeed. There's nothing in principle that forbids it. It's just that the processes by which these are made don't seem to be ones which would scale very well to the enormous areas that we're looking for. So in fact, we have issues of the scale of production versus the efficiency of the device. So what you have basically, this is just meant to show the kind of vacuum deposition system that you would use for making one of those multi-gap semiconductors. It's a really complex, cumbersome kind of piece of instrumentation. This fellow is really suffering trying to hold it up. And the idea is that if you go to this kind of processing, you can make an efficient solar cell, but it really doesn't scale to very wide areas. And that's, in a sense, in exact contrast to, for example, if you were trying to make biological approaches to this. I won't describe all the results here. This is going to be Jay Kiesling's job in a few weeks. But I'll say that the power efficiency for photon to biomass, to cellulose, from photon to cellulose, is about a few tenths of a percent, say 0.3% or so. And then, of course, you have to go from there to, say, ethanol to break it down in order to make a fuel. So you could say these agricultural approaches are scalable, but they just don't make high enough efficiency. So we can make materials that are efficient but don't scale, or we can plant crops which are scalable but not efficient enough. And we're sort of caught somewhere in between. And so there's the conundrum, and there's where you have to try to break out of it somehow. So the question is it possible to mass produce solar cells? So some years ago, Alan Heeger introduced the idea of trying to make a plastic solar cell, a solar cell completely out of plastics. And we're going to follow on some of those ideas today. And the idea would be, rather than producing a semiconductor material like those crystals that you saw, those hard kind of big crystals of silicon, perhaps there would be a way to make a material which kind of sits in a slurry of liquid, and instead of depositing it from vacuum, you would print it the way you print newspapers. In other words, the ink slurry sheet would pass by, and as the sheet is passing by, some liquid containing the solar cell material is deposited onto those sheets and dries out. And as it dries out, that would make the solar cell. That would be the goal in this kind of an idea. And one thing to remember is that this kind of roll-to-roll or sheet printing process can really make a lot of stuff very fast. one roll-to-roll kind of printing press type machine can make more solar cell than all of the existing solar cell fabrication machines that exist now. So if you could print, it could scale to enormous areas, and that could help solve the problem. Now, the question is, what are you going to print? So, for example, you might try to print plastic, but what I'm going to suggest to you today is a different idea, which is to try to print really tiny crystals, because very small crystals can dissolve inside of a liquid and then be deposited onto a substrate through a printing process. And that's the idea that I'm going to try to show you. So we're going to talk now about nanocrystals. So now we're going to take a little excursion into the past, and pretty far past. We're going to think for a moment about probably the first nanotechnologist, and that's Democritus, okay? It's going to help us think about working with really small crystals. That's what we're going to try to do here. So let's go back to Democritus, who actually was the first person to conceptualize the idea of the atom. And he came to the atom by thinking about the idea of successive division. So let's just back up for a moment and think about that. What Democritus thought about was, let's take a piece of matter. I'm just looking at matter that's someplace in the world, and let's take a piece of gold, for instance, and imagine just cutting it into two. So it's now two pieces of gold, each one half the size. And imagine measuring a property of that material. For example, you might measure its how much it conducts electricity, or its melting temperature, or how hard it is. Okay? And any of those kinds of intrinsic properties of gold should be just the same for the little piece as they were for the big piece that you started with. Now, imagine doing that again. Cut it in half and keep cutting it in half over and over and over again. And somehow Democritus intuited the idea that if you keep doing this successive division over and over again, eventually there would be kind of a graininess to matter. Matter isn't truly continuous, it's discontinuous on a very small scale. And if you keep chopping it in two, eventually, he reasoned, you would get down to a size that is, quote, indivisible. Atom, in fact, means not divisible in Greek. It would be a size at which you couldn't cut it down to a smaller size anymore. It would be truly grainy. And in fact, that's true. Everything we know tells us that if we keep chopping matter up into smaller and smaller pieces, eventually we reach the indivisible. The question is, what happens in between a really big chunk and this atomic one? In between, you get little crystals, which you might be able to say have 10 atoms across or 5 across and so on. And you remember I told you a moment ago that if you take the piece of gold and you look at it and say it's 100 atoms across and then 50 and so on, then the properties would be the same. Well, that's not true when you get down to really small sizes. If you look at a crystal that has, say, 1,000 atoms in it versus 500, and it's gold atoms, and you measure, for example, their melting temperature, they're not the same anymore. So when a crystal gets small enough, then when you perform successive division, in fact, it's not quite yet an atom, but still, as matter gets grainier and grainier, and you get down to smaller sizes, then the properties of matter change as a function of the size. And Democritus somehow intuited that. It turns out that today, we see that in real-life action in the computer industry. You'll know, of course, that if you fabricate computer chips, they're made by patterning onto silicon wafers very small transistors. And originally, those transistors, when first made, were moderately large, meaning there were enough atoms in one you wouldn't bother to try to count them. Okay? But today, as you start to make those feature sizes smaller and smaller, actually, you probably could count all the atoms in one of the little elements of one of the transistors. There'd be enough time in the day for you to actually sit down and count them all. And in fact, every time you make them half as large, I think of that as being, finally, we've gotten around to actually doing Democritus's experiment. We take pieces of silicon and cut them in half, and we are in fact at the point where we start to see all kinds of graininess and special effects coming in when the feature sizes get to be so very small. So that's a kind of an interesting point about where we are. Now, as I've mentioned to you, the properties of matter start to change as you make materials smaller and smaller. And those material property changes follow what we call simple scaling laws, little estimates for how the property of the matter change as a function of the size. And there are many scaling laws. For example, melting temperature is one I'm going to tell you about momentarily. Band gap and energy level spacing is another one that I'm going to tell you about, and that will be very germane. Hardness, the hardness of a crystal will change. Magnetism. Let me just show you one scaling law. It relates to magnetism. It's not related to solar energy at all, but I thought I'd give it to you as an example because it gives you a feeling for how the field of nanoscience is one which we're learning now, but which has been used in nature forever, so, or at least for a very long time. This would concern magnetism. Imagine that you have a very small magnet, okay, and you keep making them smaller and smaller through successive division, and you go and you align the magnet. So you put out a big field, and the magnetic moment is aligned now, it's magnetized, okay, and then the crystal gets, as the crystals get smaller and smaller, you could look at what we would call the kind of magnetic relaxation time. That is, once you magnetize the crystal, if you take away the magnetic field and just wait, eventually it will wander. The magnetic direction will get lost, and it won't remember which way it's pointing. That's a collective property of the crystal, so as you add more and more atoms to it, the magnetization will last longer and longer. In fact, it depends exponentially on the volume. Well, that means that if a crystal is really tiny, it will wander very quickly, its magnetic moment. If it's really big, it will stay locked forever. And there's a kind of crossover size at which it will retain its magnetization for a really long time. And it turns out that if you take iron oxide as an example, it's a magnetic material, that time scale over which the magnetic moment will stay locked for a really long time at room temperature is 25 nanometers. If it's less than that, it will tend to wander very quickly. If it's much bigger, it will stay locked for a really long time. Well, it turns out that in nature there are these bacteria which have inside them little magnetic crystals. Now, it turns out that those crystals are in there because they'll line up one magnetic moment to the next and make a little compass. Now, you might wonder, why does this bacterium need to have a compass inside? Well, it does gain an evolutionary advantage because there's a magnetic field of the component of the Earth that's vertical to the ground. So this magnetotactic bacterium, it turns out, can swim along that field line and go up and down. And it's not wandering and wasting its time it's moving only vertically. And it turns out that the oxygen and other nutrient levels depend on the depth. So that bacterium can swim up and down and not be wasting its time swimming sideways until it finds the optimum concentration of nutrients at which to thrive. So it builds a little compass inside there, and that compass, it turns out, is as good a one as any nanotechnologist could ever make, because each little magnetic crystal is 25 nanometers in size, which is exactly the size of the magnetic moment that will stay locked for a really long time at room temperature. And it builds a little chain out of those. It doesn't waste any material, and it's a really wonderful example of nature using nanotechnology. We would like to learn how to do tricks like that. Now, scaling laws are all important in this business, so let's think about a scaling law here, and this is going to be a scaling law that you're very familiar with. You go to the jewelry store to buy a diamond, okay? And this is from the De Beers website. It tells you right there. Big diamonds are much rarer, so a diamond of double the weight costs around 4 times more. That is exactly your experience. If you go into the jewelry store, you are forced to make a compromise based on your budget within any quality of diamond that you're interested in. Very rapidly, you're forced into a certain size within your budget because of this fundamental scaling law of the price scaling like volume squared. Now, where does that come from? Well, it's very much related to the solar cells where that comes from, so let's think about it for a moment. Imagine a crystal that's trying to form, and it's a crystal that, as the atoms are adding into it, somewhere a mistake is made. So one atom doesn't go in quite the right spot, and then there's a defect all through that crystal. And now you'd like that defect to go away. So the only way for that defect to go away is to heat the crystal up and anneal it and shake it, if you like. All the atoms will shake around, and eventually the defect will exit. I had a movie showing melting, but we had a little computer event here earlier, so there's no movie. But you could imagine that a crystal, when you warm it up, the defect will eventually tend to leave. But again, how long that will take will depend critically on the size of the crystal. The bigger the crystal is, the longer it will take to anneal out that defect. That's why perfect diamonds are so rare, because they're really big, and in order for them to be of high quality, they have to be really perfect. So you have to wait a long time for the defects to anneal out. That's a basic fundamental property of crystals. It turns out that the relaxation time for pushing out a defect goes something, again, exponentially like volume. So now imagine that you have a really little crystal. Instead of being the size of this one, which is so many atoms across you could never count them, say it's only 100 atoms across, well, that one should be pretty easy to push the defect out of. Just warm it up for a little while, and it will probably become more pure. Now, if you think about what we're trying to do today, when we make our solar cells, it's like trying to make big, gigantic diamonds to coat your rooftop, okay? We're trying to make crystals that are highly, highly perfect and then slice them up and coat them on your roof, okay? So that's one approach, and it's got the advantage that it has worked already. So there's a big advantage to that. The only problem is you're making enormous crystals. This one, for example, is a 12-inch crystal, and that's kind of a typical silicon ingot that you could make. Now, instead of that, you could make these nanocrystals. Here you see a very small crystal, and here you see you can count the number of atoms across, okay? Well, if you think about it, instead of trying to coat our roof with giant crystals, instead we could turn that on its head and say, let's try to make the solar cell out of the smallest possible crystals that could still work as a solar cell. So we'll try to think about how small we could make it. Why would you do that? Well, because really tiny crystals you could just cook in a vat, in a liquid, and you'd only have to warm them up for a short period of time, and they could become highly perfect. So you would make the problem easier. And so these are just examples of very small crystals of different sizes and shapes, and that's basically the essential idea that underlies a lot of what we're interested in doing. Now, there's another part to that. So that's a conclusion there, is that by going to very, very small sizes, the fabrication gets very easy. Maybe a little counterintuitive, but it's true. You can grow the crystals under very modest conditions, and they'll become very perfect. Instead of trying to make giant diamonds, you just make ones that are just big enough for the purpose that you have in mind. Now, there's a second aspect of it, which has to do with energy levels. And you'll recall I told you about how the energy of the photon is stored in the semiconductor material, the analogy to taking the ball and throwing it up. It hits a wall and falls down that wall and goes to the ledge, which is up high somewhere, and that energy is now stored as energy inside that material, okay? Well, there's a real key difference between doing that in bulk crystals, big ones, and doing it in tiny ones. That has to do with the nature of the energy levels inside the different materials. So, for example, if we look at a really big crystal, all the energy levels are completely continuous. Okay, so there are many, so if I throw the ball here, it can fall down this ramp to this point and then stop. If I have a really atomic system, the energy levels are actually discrete, very specific energy levels. So instead of having a wall with one shelf, there are a series of very specific shelves that you can throw balls onto and catch them there. Okay? And that's a key difference between a bulk material and a little crystal. And so maybe hiding inside here somewhere is a way, if I make a material 3 or 2 or 1 or quote 0-dimensional, if I make it different shapes and very small, there's a way of changing the distribution of electronic energy levels in a way that might allow us to harvest the energy more efficiently. And you'll recall what I told you. This is throwing the ball up, and then it falls down to the ledge. And with the reason that it can fall down to the ledge is because these energy levels are continuous in a system that has a huge number of atoms inside of it. On the other hand, we could have a system like this. Imagine a really tiny crystal with discrete energy levels instead of continuous ones. When light comes in and gets absorbed and the electron is kicked up to this level, it might be possible to actually just pull the electron out before it has a chance to fall down, because it kind of sits on that temporary ledge for a little while. Okay? That would be collecting what's called a hot electron. Now, you can imagine collecting a hot electron could work in a really small crystal because the electron doesn't have to go very far, so it might not lose its energy to heat before you've had a chance to pull it out. And that would be collecting a hot electron. Or shown on here is another idea where you come in and excite one electron, which has a high energy, and instead of falling down to this level and losing its energy as heat, it actually can excite other electrons in the system and make several electrons. So when a photon gets absorbed, instead of getting one electron in current, you might get two if it's a high enough energy photon. That too is something which can happen in a very small quantum system, which is very difficult to achieve inside an extended crystal. So the idea is that there are many schemes out there for harvesting solar energy and losing less of the energy of the light to heat when the system consists of very small crystals as compared to extended ones. On the other hand, there are problems which appear when you try to make a nanoscale photovoltaic. For example, in a bulk crystal, an electron can just move a very long distance on the scale of electrons at least. It can go a very long way before anything happens to it. Whereas if we break the crystal up into lots of little pieces, then the electrons have to hop from one little piece to the next. So this, if you like, is one of the conundrums of nanoscale photovoltaics. It's a lot like many aspects of the world we know. There is often a conflict between the individual and the collective. In this case, what you would like to do is make very isolated energy levels in a small region of space, because there you can manipulate how the energy is harvested. Okay? But then afterwards, you want the energy levels to be such that you can just collect the charges very easily. So you want something that's isolated on the one hand, but well coupled on the other. And those are kind of things which fight against each other a little bit. So I'm going to show you two examples of little solar cells, and we'll see what they look like. Here's one where we took some rods of semiconductor and just dispersed them inside plastic. So it's just a spin cast stuff of crystals inside plastic. And what we found is that we could make it out of little crystals, larger ones, or even larger ones. And as we went from little crystals to bigger rods to longer rods, the performance of these devices got better and better with the longer rods. That's because, going back to this one, with the little crystals, the charges had to hop too many times to get out, and as we made them from dots to rods, they got better because they didn't have to hop so many times as they went through the device. These are solar cells that are processed completely from a liquid solution, just like an ink, in the way that I was describing to you earlier, but they have kind of a disappointing power efficiency because lots of problems haven't been solved, and there's lots of interfaces still. So they don't perform as well even as a conventional solar cell quite yet. Another approach is to make these kind of branchy crystals. So here are some crystals that have lots of branches in them, and these could be networks that charges could move through, and they might balance out this idea of localized regions where light gets absorbed versus regions where charges get transported easily. And so here, just take a look. This is a branchy crystal at one moment during its growth of a semiconductor material, and this is at a next moment, and then a minute later, and you can see they make kind of these what look like kind of thorn balls. But if you look at the crystals more carefully, oops, I don't know if it's going to play. No, it's not going to play on there. If you look at these carefully, you can see that the branches are not randomly distributed. In fact, there are these really large branches and then finer and finer ones. And if you like, that looks a little bit like our road system, where we have really large freeways and then more local and local roads. And the idea behind a solar cell like this would be that this branched crystal, the charges would be generated at all the fine little branches, and then the charges would get harvested in towards the larger and larger ones and ultimately collected through the kind of superhighways. If you like, the fine branches are where we confine the charges to get discrete energy levels, and then they're naturally coupled to superhighways that bring the charges out and collect them. So it's a kind of effort to make a material that balances out the need for localization to get control over the energy levels with the ability to move the charges rapidly. There are many other related ideas. Here you can see solar cells which have been made with little crystals that are very small in size but have been made to couple to each other very strongly, a lot like some of those cartoons that I showed you. Or here are other ideas in which we have little dot-like crystals that have formed spontaneously inside a wire. So this is another solution to the problem, how can I localize charge to control the energy levels, but then somehow attach it to a wire so that the charges will be moved out very quickly. Now, another aspect of the work, you can't really see this slide, and that's okay, I'll explain things to you, but another aspect of this is, if you recall, I mentioned to you very early on in the talk that some of the highest performance solar cells made for satellites use materials which, if you were to take all of that element that exists in the world, all of it that is out there, and make solar cell, it still wouldn't be enough. Okay? So that's pretty important. If you're going to make a solar cell in an enormous area to really solve the energy problem, you've got to make sure there's enough of it. So here, for example, we've taken every binary material and just investigated it and said, that means it has two elements in it, every possible one you could make a solar cell out of, and said, okay, take all of it, make a solar cell out of it at a certain efficiency, I think in this case it's around 10% power efficiency, and then see how much energy you can get out of it. And so this is how much you need to power the United States, and this is how much you need to power the world. And you can see some materials, even if you took everything, there's just not enough there. So X, okay. I mean, you can make a solar cell out of this for learning, but not for really solving the problem. So you're forced towards this side of the area where there's lots of these materials, like iron sulfide. Now, iron sulfide is an interesting example because in the 1960s it was discarded as a possible material for making solar cells because they couldn't control the material well enough to dope it NNP, to make high quality, and so on. But it turns out that when you work with nanoscale materials, as I was mentioning to you earlier, they're much easier to fabricate. So something which we might have rejected earlier, now we could revisit. And there's an interesting example on here. I won't go through the details of it, but for example, zinc oxide and zinc sulfide. These are very benign materials that are very, very abundant. The only reason you can't use zinc oxide as a solar cell is because it's a semiconductor material. That's good. But the shelf, the gap of levels, is so big that all the visible light goes through. So not a very good solar cell material, even though it's very abundant. So that's true also of zinc sulfide. It's not a good material for making a solar cell. But it turns out that if you take the two and you mix them together on the nanoscale, so here's a crystal that's zinc oxide in the center and zinc sulfide on the outside, when you mix them together, their energy levels change a little bit, and in fact, they now suddenly have a lot of absorption in the visible region of the spectrum because the energy levels jump from one material to the other. The occupied electron jumps from the zinc sulfide into the unoccupied levels of the zinc oxide. So the shelf, instead of being way up here, is now just over to the side and not too much higher. So you can take these materials and mix them together and suddenly get a material that absorbs in the visible region where before it didn't, and that might be a good material for making a solar cell. So this is the kind of exercise that we're going through, trying to evaluate all the possible materials, even ones which had been thrown out earlier, because now there's new ways of patterning them that might work. Now, as I've mentioned to you, there are existing solar cells. You can make them today. You can buy them and put them on your roof if you like. The only thing is, as I'm sure you've noticed, we can't quite make enough of them, okay? And that's our constraint in this case. We can't quite make enough solar cell. Here's an example of another technology. This is the color televisions. And you can see here that there was what's so-called learning curve for color televisions. This shows the experience in Japan and in the United States for color televisions made with transistors. And you could see this line here. And in fact, you could follow this line for a very, very long time, and it would sort of be roughly similar. And then in 1970, the Japanese started to make transistor-based color televisions instead of vacuum tubes. Here's vacuum tubes, here's transistors, and you can see that in 1 year there was a huge jump. All of a sudden, the technology just changed, and after that, they were on a new curve. So there was one curve, and they were kind of tooling along, and then a new technology came in. Now, in many ways, this is a color television, and this is a color television, and they both were color televisions, but when the curve changed, lots of things got much better, okay? And in many ways, that's what we would like to do with photovoltaics. We're making solar cells today, and as you make more and more of them, we do get better and better at making them, and they do get cheaper and cheaper, and everything is going along just fine. And if you like, we could choose to just stay on this curve, and it would get better and better for quite a while. Eventually, it would saturate, but the problem with that is if we just stay on this curve and we ask how long is it going to take before we can make enough, a large fraction of our energy from that technology, it's longer than we'd like to wait. It's a lot longer than we'd like to wait. It might be another 30 years. And we don't have 30 years. If you were at Steve's talk, you can appreciate that. And if you read the newspaper even, you can realize we can't wait that long. So we really do need to jump curves to another one. And we're hoping that the nanocrystal photovoltaics would be an example of jumping to another curve. It's not that it would suddenly execute some completely new function. It's just it would be made in a different way. And because of making it in that different way, it might be that it could scale to a much, much larger area because nanocrystals can be made much more cheaply than big crystals. And they could be processed from solution and spin cast. And maybe even they'd show some new physics which would allow them to have even better performance. Now, I did tell you that the goal of the project is not just to make electricity, we have to actually make a fuel. And I'm not going to cover that today, but I'm just going to make a couple of kind of very introductory comments. Imagine that this is a little piece of nanoscale photovoltaic. It's a little semiconductor rod, say, with metals attached to it, and light comes in and gets absorbed, and the electron gets collected, and the emptiness of an electron, a hole, goes the other way, and those two get collected. Now, what you could imagine doing is taking all of these and embedding these little small electron manipulators, if you like, photon absorber and electron harvesters, and putting them in a membrane, and then attaching to them molecules which could perform chemical reactions. Then that would be an example of us making an artificial leaf, okay? It would be a material made out of all inorganic-y kind of stuff, but it would perform the functions that a leaf performs in the sense that it would absorb the light, harvest it, and then perform a chemical reaction to store the energy in a chemical. So there are different ones that you can use. For example, you could split water. This is the easiest reaction to do, quote, the easiest one to do, which would be taking water, absorbing the energy of the light, and converting it into hydrogen plus oxygen. And then hydrogen is your fuel. Now, there's lots of issues with hydrogen that we could talk about, but the first thing you'd like to do is just make a system which could easily take the energy of the light and break the water apart and make the hydrogen. Then you have other problems like can you store the hydrogen, and once you've stored it, can you get it back out, and things like that. But we'd probably be happy if we could just do this part really well with a chemical system that operates in a simple way. So we'd like to know if we could do that. And another reaction that we would like to do, which is what I was telling you earlier at the beginning, we'd like to be able to take a more complicated reaction like carbon dioxide, react it with water, and make methanol or some other kind of stored fuel. And again, you're taking the energy of the sun and you're raising the molecule up to a higher level. Now let me make an analogy. I've talked to you earlier about throwing that ball up and it hits the wall and then it falls down to the ledge and it stops on the ledge, and now we've collected that, and anytime we want we can just tilt the ledge a little bit and the ball will fall down and we'll collect the energy. Okay, that's what we did with electrons. Now we'd like to do something like that with molecules and chemical bonds. This is one energy level, and here's another one. This is up at a much higher energy, and the difference between those would come from absorbing the energy of the light and taking us up to this higher level. To do this, though, is a lot harder than what I was just describing with respect to storing electrons. Just pulling an electron out of a crystal and then making it conduct and then become part of a circuit that electrons can move around in is actually simpler than making and breaking very complicated chemical bonds, which we're not yet quite as good as doing as we would like. So here's an example of such a thing where we would take water and just this is the oxygen evolving part, then there's a hydrogen evolving part on the other side. And you can see these make very complicated little chemical reactions. For example, we might have a reaction like this one where we've got these ruthenium atoms which act as the catalysts. What does a catalyst do? Well, remember, we want to go from the energy of the water to this energy, which is up higher. It's a lot like, it's an awful lot like crossing a mountain pass, okay? So you're sitting in one plane, and there's another plane that's up a bit higher, but in between them, there's a very complicated terrain that's like a mountain pass. And if you don't have a good guide, you're forced to go over the peak of the mountain pass. That would be a way to get from here to there, but by the highest energy approach. You might say, why does the energy go up at all? Well, in order to form new bonds, you've got to break some of the old ones first. So the energy has to go up first, then come back down again. And so if you have no good mountain guide, you end up not knowing which way to go and you follow a bad path. But if you have a catalyst, that's like your mountain guide. It helps you pass by the most efficient path to go from one to the other. That's a molecular catalyst. And our goal is to try to make good catalysts, but it turns out we're still not too good at it. So for example, imagine this one. Here's a catalyst that has some metals in it that are rutheniums, and here's one that contains 2 oxygens, and a water comes in and binds to it. There's HOH, so that's H2O if you like. It comes in and it binds in this way, and then you could imagine another water coming in such a way that an oxygen gets eliminated, and around, and you could follow a cycle. This is kind of a molecule which helps the water atoms rearrange and go from being H2O to oxygen and ultimately hydrogen. This is an example of such a catalyst from nature. Remember, we always try to compare it to nature. Here's an example of such a catalyst from nature, which contains manganese and oxygen and calcium in just such a way. And this one operates at a turnover rate of 300 per second. What that means is that each one of these proteins in the oxygen evolving complex in photosystem 2, in a living system, each one of these molecules will turn over 300 oxygen atoms per second. Well, here's a catalyst that somebody made in a laboratory, kind of, quote, bio-inspired with some of the same atoms inside of it, and it has a turnover rate of 11 per hour. So you see, 300 per second versus 11 per hour means that we have a ways to go in terms of learning how to make really good catalysts, and we have to learn how to do that. And that's one of the goals that we have. So what I've shown you is a little photovoltaic, and maybe if we knew enough, we could connect it to some catalysts that would evolve hydrogen on one side and oxygen on the other, and we could collect them. And if you like, what we do is we spend a lot of our time looking at how photosynthetic membranes work, in which very complicated chemical transformations are performed every day inside our bodies and inside leaves, where we see very complex chemical reactions going on either side of a membrane. And that's what we're trying to mimic inside a system that's made completely out of artificial material. You might say, why not just use these? Well, you can, but these don't quite have the power efficiency we want. These have high power efficiency, but we can't quite get all the chemical transformations to work as well as we want. So again, that's the conundrum that we're trying to work our way through. One theme that I want to leave you with before I conclude is that on the nanoscale, we have what we would call a conjunction of soft and hard matter. Here's a picture of a protein with a channel inside it, and it's one that's used for transporting molecules across a membrane. And you'll notice here that in nature, this unit, which has a lot of chemical complexity to it, is a few nanometers in size. It's got, several hundreds of atoms in it. Here's one of our little nanocrystals, and this is the kind of material which we might make, say, a light-emitting diode or a solar cell or some kind of active electronic solid-state element out of. But when it's a nanocrystal, again, it's only a few nanometers in size. And so one of the things that has scientists very intrigued is the fact that these kinds of components out of which we make our artificial technologies and these kind of basic building blocks out of which nature makes functional units are now about the same size. And so there's a lot of opportunity for one to learn from the other about how to make new materials. What I've tried to show you a little bit about is the problem of how we could one day try to make a system which could take, for example, carbon dioxide and water and ultimately make, say, methanol. And there are many paths from here to there. And I don't want to give you a feeling that we're not optimistic. Let me say that, for example, with respect to the photovoltaics and making electricity, the good news is we already can do this at quite high efficiencies. The only problem is we quite don't know how to make it scale to a large enough area, which isn't the worst of problems to have. And we're learning quickly how to make these things out of nanoscale materials, which presumably can scale to much larger areas. And I talked to you a little bit about this problem of artificial photosynthesis, but even if we didn't quite learn how to do it photosynthetically, there certainly are electrolytic ways by which we could, for example, split water pretty efficiently. So there are many ways to make our path from here to there, and they involve some very interesting intersections between science and technology. And let me thank you for your attention.